Welcome to The Explainer. Today, we're talking about one of the internet's core protocols. But here's the twist. It's powerful not because of what it does, but because of what it doesn't do. I mean, this thing powers your video calls, your online games, and its story is just a total masterclass in brilliant, minimalist design.
All right, so let's just jump right in with a question that sounds kind of backwards, right? Why on earth would you go and design a fundamental piece of the internet to be intentionally unreliable? It seems crazy, but the answer is actually where all the genius is hiding.
So look at it this way. On one hand, you've got TCP. It's the internet's super dependable workhorse. It bends over backwards to give you this whole list of promises, making sure your web pages and emails show up perfectly. Then, on the other hand, you've got UDP. It looks at that exact same list and just says, yeah, not doing any of that. And believe it or not, that's not a bug, it's a feature.
And this whole less is more philosophy isn't an accident. It goes way back to 1980 to a guy named John Postal. See, the designers needed something lean, something fast, a lightweight alternative to all of TCP's complexity. They wanted a protocol so simple that, as the legend goes, you could sketch out the entire thing on a cocktail napkin. And now, that simple little idea powers a massive chunk of our digital lives.
So to really get UDP, you got to wrap your head around this one key idea, the datagram. See, a TCP packet is like a single page in a numbered book and needs the other pages to make sense. But a UDP datagram, it's more like a postcard. It's totally self-contained. It doesn't know, and it definitely doesn't care, about any of the other postcards sent before or after it. It just exists on its own.
And this slide right here, this is the proof in the pudding. I mean, just look at the difference. A TCP header needs 20 bytes, sometimes more, for all of its machinery. Sequence numbers, acknowledgements, all that stuff. And a UDP header? Just 8 bytes. That's it. It is literally the definition of minimal overhead.
So this is what you get for that tiny header. UDP doesn't promise your data will get there. It doesn't wait for a thank you message. It doesn't resend lost packets, and it couldn't care less about the order they arrive in. It is a true fire and forget system. Which sounds kind of risky, doesn't it? But as we're about to see, for some things, it's exactly what you need.
So, where is this so-called unreliable protocol not just a good choice, but the only choice? Well, it turns out there are a whole lot of situations where TCP's incredibly helpful guarantees would actually just completely ruin the experience for you.
For instance, take DNS, the internet's phone book. Use it 100 times a day without even thinking about it. All it does is ask a simple question and get a simple answer. With UDP, it's one quick trip, there and back. Boom, done. But with TCP, all the handshakes and goodbyes would turn that into 4 separate round trips. For quick jobs like this, UDP is just way more efficient.
And this quote just nails it, especially when we're talking about voice and video calls. Think about it. If a tiny little piece of audio gets lost, TCP would grind everything to a halt to go get it back, causing a noticeable freeze. But with UDP, the app just says, oh well, and moves on. Maybe you get a millisecond of silence you don't even notice. You'd always rather have a tiny, invisible blip than a big, jarring freeze. Timeliness is king.
It's the exact same story for online gaming. Imagine another player is running across your screen. A packet with their position from a split second ago gets lost. TCP would literally freeze your game while it tries to recover that old, now completely useless information. But UDP? It just shrugs, drops it, and uses the next packet that arrives with the player's new position. Waiting for stale data is always the wrong move.
But UDP's beautiful, simple, connectionless world was about to collide head-on with a massive problem. A problem that came from a temporary fix in the 90s that, well, it never went away. And it became UDP's #1 enemy. Network Address Translation, or as we all call it, NAT.
So here's the backstory. Back in the early 90s, people realized, we're running out of IPv4 addresses. So NAT was invented as this clever stopgap measure. It let all the devices in your home, your laptop, your phone, everything, share one single public IP address. And you know what? It worked so well that this temporary patch is now built into basically every single home and office router on the planet.
And here's the absolute deal breaker for UDP. When your friend's game tries to send a UDP packet directly to you, it hits your NAT router first. But since there's no formal connection, your router has no idea where to send that packet. Should it go to your laptop, your phone, your smart TV? It has no clue. So it does the only safe thing it can do. It just drops it. For pure peer-to-peer UDP, NAT is basically a brick wall.
So how did the networking world get out of this mess? I mean, how do we make this work? Well, it wasn't one single magic bullet. It's actually this really clever, three-layered strategy to get UDP through our NAT-filled world. Let's break it down.
Okay, so the first hero in our story is stun. It's a pretty simple but genius trick. Your computer sends a quick message out to a public stun server. That server then replies and tells you what your public IP address and port number look like from its perspective, out on the public internet. It's kind of like holding up a mirror to see your own face.
Now, stun is great. It works most of the time, according to Google's data, about 92% of the time, in fact. But what about that other tricky 8%? You know, the connections that are stuck behind really strict corporate firewalls. For those, we need a plan B. And that plan B is called turn. Instead of making a direct connection, turn acts as a middleman, relaying all the traffic through a public server. Yeah, it's slower, it's more expensive, but it almost always gets the job done.
And finally, there's ICE, which is basically the conductor of this whole orchestra. It's the system that puts everything together. Each device gathers up all its possible addresses, its local one, the one it found using stun, the turn relay address, and it shares this list of candidates with the other person. Then, ICE just methodically starts trying them all out, from best to worst, and the very first one that works wins. It's a really elegant system that just finds a way.
So, all of this brings us to a really important point. Choosing to use UDP isn't a free pass to just send data wildly. By ditching all of TCP's built-in safety nets, you are basically signing a contract. You, the developer, are now personally responsible for dealing with all the messy realities of the internet.
And there are official guidelines that spell out the terms of that contract. You have to handle your own rig control. You have to be a good citizen and not clog up the network. You have to worry about packet sizes, and on and on. This is serious stuff, and it's exactly why frameworks like WebRTC are so important. They do all this heavy lifting so you don't have to.
And you know, this quote really is the best way to think about it. UDP isn't broken or incomplete. It's a fundamental building block. It's a blank canvas that gives you the total freedom to build only the features your application actually needs and absolutely nothing more. Which leaves us with one last thing to chew on. The story of UDP is just this powerful reminder that sometimes, in engineering, and maybe in a lot of other places too, true elegance and innovation don't come from adding more and more features. They come from the very deliberate, very purposeful act of taking things away.